integrated.
Hello guys, and welcome back to the PyTorch tutorial series. In this video we're going to start to discuss about optimizers. And optimizers are one of the most fundamental concepts in deep learning. So in this video we're going to go in depth in order to understand the different kinds of optimizers used in deep learning, and later on we will try to implement them using PyTorch. Before we delve into directly to optimizers, first let's start by defining the major machine learning building blocks. So when we talk about machine learning or deep learning, which is a specific type of machine learning, we need to talk about these concepts. So normally a deep learning neural network is a complicated version of a single neuron. So it tries to imitate the functioning of the neurons in the human brain. But in this case, we're trying to use mathematical functions which takes in input signals and tries to produce an output. And any kind of sophisticated deep learning model is just the stacking or the multiple use of these mathematical functions to solve complex problems. So the first thing is inputs or features. So inputs or features are known as attributes and values finally used for training. For example, temperature can be an attribute, and temperature is equal to 25 degrees Celsius is a feature. So the first thing that we need when we try to build a machine learning model is the input. And the inputs might be characteristics or attributes that describe an entity. And these can be in different dimensions, starting from scalars to higher dimensional vectors. And a feature vector lists all the features that are fed into a machine learning model. So a vector is mainly used to represent higher dimensional attributes. The next one is a hidden layer, and it's mostly composed of a mathematical function. And layers in between the input and output layers in a neural network are known as hidden layers. And they're mostly found between the inputs and the outputs of our model. So a model is the output of any ML algorithm run on the data. It is a data structure that stores weight and bias matrices containing the learned parameters. So a model is composed of mathematical functions, and the purpose of a model is to learn from the input data and update the parameters of the model. So it is composed of weights and biases, and these are parameters that we try to adjust so that our model can adjust to our input data and produces the specified output. So another thing that we need with respect to our inputs are labels, and the output data is used in training a supervised learning model. For example, if you want to train a cat classifier model, we need to prepare a dataset in which we label the image by saying whether it is a cat or not a cat. So if the purpose of this model was to classify whether an input was a cat, an input image was a cat or not, first you need to fit in the label associated with each data saying that it's a cat or not a cat. First, let's try to understand the PyTorch workflow. So far we have covered loss, and we have seen how to compute predictions and compute gradients. In our video about loss and gradients, we have discussed these concepts in detail. So the training pipeline, when you try to build a machine learning model using PyTorch, is basically the same. The only thing that you change might be the complexity of the model, the type of loss function that you use, and the type of optimizer that is used to update the parameters using the computed gradients. But this training pipeline doesn't change a lot, so the only thing that you need to memorize when constructing any machine learning model using PyTorch is to follow this workflow. The first one is preparing the data, and we haven't covered this concept, but in PyTorch you can prepare your dataset using the classes dataset and data loader. These are used mostly to organize your dataset so that it can be ready for training the machine learning model. Notice that the data that you use from the real world is not organized, and mostly it's not useful for the model to learn something new. So it must be normalized or organized, and these helper functions they will help us to organize our data, and we will cover this concept in detail. The second one is to design a model. We need to pick a model, starting from the simple models like linear or logistic regression up to complicated neural networks. Third is we need to construct a loss, and we have seen a lot of options for the losses that can be used using PyTorch. For example, we mentioned the mean squared error. Fourth, we need to construct an optimizer. So this is going to be basically the topic of our video. In this video, we will mostly talk about optimizer. And for example, we can pick a gradient descent, which is one type of optimizer. Fifth, we need to construct a training loop, and this loop goes from 1 up to 100, or basically any type of numbers that we select for the number of iterations or epoch. So when constructing a model, the first thing that we need to perform is forward computation, or a forward pass. This helps us to compute the outputs from our model. So as we go from left to right in our model, this is known as a forward pass. And we have seen this in detail when we discussed about how to construct computational graphs. But here basically we can use our model to receive an input and give a prediction. After we move forward, then we need to compute the loss. Once we get the output from our model, we need to compute the difference between our predictions and the labels. These are the target labels that are associated with our input data. Then after we compute the loss by using the PyTorch loss functions, then we need to move backwards. So once we move forward, then compute the loss, then we need to move backwards. This is known as a backward pass. And this helps us to compute the gradients that we have discussed in a previous video. And the purpose of an optimizer, which we constructed here, is to update the weights by using the computed gradients from the backward pass. Remember that we used the backward function in our video about loss in order to move backwards in our computational graph and compute the gradients for our parameters. Then optimization algorithms use these computed gradients in order to update our weights. So we haven't covered the optimizer part and how to construct a model and how to prepare the data. But this is basically the workflow for any kind of PyTorch model. So let's try to see a diagram which represents the workflow in PyTorch. First, we need to get the data ready. Then we need to turn them into tensors. The basic data structure for PyTorch is tensors, so we might have NumPy arrays, unstructured data or images, but we need to convert them into tensors so that they could be used for our PyTorch model. Second, we need to build or pick a pre-trained model. We need to construct our model by using the pseudocode that we used here. And we need to pick a loss function and optimizer. Then we build a training loop. And this is basically the main thing that we need to focus on when we are building a PyTorch model. Then once we fit the model to the data and make a prediction, we need to evaluate the model. We haven't reached this step yet, but in the next videos we're going to see how to evaluate a model. Then we need to improve through experimentation, and finally we need to save the trained model so that it could be ready for production or shipped off to another domain. Once we have covered the PyTorch workflow and basic concepts for building machine learning models, we need to understand the difference between parameters and hyperparameters in a neural network or a machine learning algorithm. So we have seen features and models and also outputs, but another thing that are associated with our model are parameters and hyperparameters. So parameters are variables whose value we learn from training any machine learning model, and these are the weights and biases in neural networks. So, and hyperparameters are parameters whose value is used to control the learning process. So parameters are basically needed for making predictions, and these are trained together with our model. The purpose of creating a neural network algorithm is just to initialize the model first with random parameters, and then when we train the model, these parameters can be optimized by computing the gradients, and once we find the correct set of parameters, then we say that our model is ready for making predictions. But hyperparameters are required for estimating the model parameters, so they're basically associated with the parameters of the model, and they're used to control the learning process. The parameters are estimated by optimization algorithms such as gradient descent, Adam, and AdaGrad. So the purpose of an optimization algorithm is basically to adjust the parameters, and these parameters are not set manually, but hyperparameters are set manually. So for example, the learning rate for a model has to be set by us manually, and the parameters can be just initialized randomly first, and they can be adjusted by using the optimization algorithms. And hyperparameters are basically parameters whose value is set before the model starts training. So hyperparameters are already initialized before we start the training procedure. But there might be some optimization algorithms who technically update the hyperparameters as we progress in the training procedure, such as the AdaGrad model. But these are some exceptions, but as overall, hyperparameters are initialized before we start the training procedure. and they cannot be learned by fitting the model to the data. So these are not going to be learned as parameters. So these are some of the hyperparameters used in different models, such as the learning rate in gradient descent. The number of iterations can also be considered as hyperparameters. The number of layers in a neural network can also be one type of hyperparameter, because we can fix the number of layers, and that shouldn't be changed as we progress along the training procedure. But if you want to create a different model, then we can just adjust the number of layers. But for one training experiment, the hyperparameters are going to be fixed. The final parameters found after training will decide how the model will perform on unseen data. So once these parameters have been adjusted and we find the correct set of parameters, then we can use these parameters to make predictions on unseen data. The choice of hyperparameters decide how efficient the training is. In gradient descent, the learning rate decide how efficient and accurate the optimization process is in estimating the parameters. So let's see how to get the parameters from a model using PyTorch. Last time in the discussion about gradients, we have seen how to convert a variable into a learnable parameter by adding the requires grad equal to true argument to the tensor function. So you can watch the video that I made about gradients in order to understand this paragraph, because we have seen how to build a computational graph, and we might have inputs and some other variables that are associated with the computational graph. If we want to turn a tensor into a parameter, we basically add the argument requires grad and set it to true. This will track and compute the gradients used for updating the parameters later on. So this variable is going to be a parameter by default in PyTorch, and PyTorch is going to track any variable which is assigned requires grad to true and compute gradients for this variable. To keep track of all the weight tensors inside the network, PyTorch has a special class called parameter. In PyTorch, we have a class known as parameter, and the parameter class extends the tensor class, and so the weight tensor inside every layer is an instance of this parameter class. So when we build a model, for example, in this case we're using a linear regression model. In a future video we're going to see in detail how to create models, but for now, in order to instantiate a model, we can use the neural network package from PyTorch and call the model that we want. And this linear model basically has some parameters such as weights and bias, and those are going to be initialized by default in PyTorch. And these parameters are basically an extension of the parameter class in PyTorch. They're an instance of this parameter class, and this is the class that we're talking about, and it extends from the tensor class in PyTorch. The following code demonstrates how to construct a module parameter known as parameter. So the neural network module has a function or module known as parameter, and this parameter is what we use in order to instantiate the parameter class. And we can see that weight is formed with a specified tensor, implying that the weight's initialized value should be the same as the tensor torch. So For example, if we create a tensor known as torch.float tensor, which is a 3x3 tensor, and we pass it inside of the parameter class, this is going to be considered as a weight or a parameter. So the first option was to pass the requires square equal to true parameter inside the tensor class in order to turn this variable into a parameter. And another option is by using the parameter function of the neural network module, we can pass any tensor inside, and this tensor is going to be automatically converted into a parameter, and all the parameter weights are automatically added to the model dot parameters function, where net is a model. So if we constructed a model and we call the dot parameters method on that model, it's going to give us a list containing all the parameters found in our model. So for this small linear regression model, we have weight and bias, and these two are tensors, and notice that it says parameter containing. The first one is the weight and the second one is the bias. And we can also, these are randomly initialized by PyTorch itself, but we can basically assign the weight and the bias by ourselves by using the state_dict function of the model. And we can call the attributes weight and bias, and by passing in the index 0, which is in this case it's a single value, but in other cases we're going to get a matrix or a vector, so we have to use indexing to access the first weight and the first bias, and we're going to change them from -5.21 to -10 for the weight, and we change -5.53 to -20 for the bias. So this is basically a short introduction about parameters. We need to understand how a model can be initialized using the parameters before we proceed and discuss about optimizers. So the objective of a machine learning algorithm is basically to reduce the difference between the predicted output and the actual output. So we might have some input features, we feed these input features into the machine learning model, and the associated weights and biases are going to be considered as parameters for these machine learning models that we use, and we get a predicted output from our model that is learned from the input data, and we have actual output, which are the labels or targets associated with the input features. And we need a cost function to tell us the difference between the predicted output and the actual output. And finally, we have to compute an error, which is going to be the difference between the actual output and the predicted output. So the cost function is the one that tells us the error made by our model. And these cost functions are mostly convex functions. As our goal is to minimize the cost function by finding the optimized value for the weights, this can be done by updating the weights using the optimization algorithms. So the goal of training a machine learning model is to minimize the cost function, because when the difference between these two becomes very small, the error will also be small, and our predicted output are actually getting closer to our actual output, which means our model is getting better at predicting the input data. And the goal of the optimization algorithms is basically to use computed gradients and update the weights so that we change the randomly initialized weights until we find the best weights to produce a cost function with less error. To achieve this, we run multiple iterations with different weights. This helps us to find the minimum costs. That's why we need multiple iterations in order to minimize the cost until we find the appropriate weights. And this is basically gradient descent. So gradient descent is basically the simplest kind of optimization algorithm. Now we have arrived at the main topic for this video, which are optimizers. Optimizers are methods that change the value of the parameters so that losses reach the minimum. And they're also used to solve optimization problems by minimizing the cost function. So they're basically used to adjust the value of the parameter so that the loss can be minimum. If we consider j of theta to be a loss function, and theta 0 and theta 1 are parameters, then this is a convex function, and the role of an optimizer is to minimize the loss so that we could find the minimum point for our cost function. Optimizers update the weight parameters to minimize the loss function, and loss function acts as guides to the terrain, telling the optimizer if it is moving in the right direction to reach the bottom of the valley, known as the global minimum. So the purpose of an optimizer is just to guide the cost function to find the global minimum. There are many different kinds of optimizers used in PyTorch and other deep learning frameworks, but in this video we're going to focus on the four kinds of the four most important optimizers used in PyTorch, which are gradient descent with momentum, atom, and RMS prop. The other ones are basically associated with the atom optimizer, but basically the atom optimizer includes all of the gains from the other kinds of optimizers. So if we discuss about atom optimizers, it's more than enough. So let's start by defining the first kind of optimizer, known as gradient descent. Gradient descent is an iterative machine learning optimization algorithm to reduce the cost function so that we have models that makes accurate predictions. It's iterative, so this is a keyword, which means that we are performing this for many iterations, and it helps us to reduce the cost function so that we can make accurate predictions. Why do we need gradient descent? In neural network, our goal is to train the model to have optimized weights to make better prediction. We get optimized weights using gradient descent. Mathematically, we randomly initialize all the weights for a neural network to a value close to 0 but not 0. So before training our model, we need to initialize the parameters of our model, and those randomly initialized weights are going to be basically close to 0 but not 0. If it is 0, if it is initialized to 0, our model is not going to learn anything. So that's what is known as vanishing gradients. and they don't update our weights. We don't also want the weights to be very large so that it doesn't lead to exploding gradients. We calculate the gradients, which is the derivative of the cost function with respect to all the parameters, and it's a partial derivative of the cost with respect to the weight. So the first step before using an optimizer is to compute the gradients by using the concepts that we have learned in a previous video. After we compute the gradients, another component that we need is what is known as a learning rate, which helps us to adjust the weights with respect to gradient descent. So the first component are the gradients. The second component is the learning rate. And once we have computed these, then the purpose of gradient descent is to use these two building blocks and adjust the weights. So we're adjusting the weights and assigning them to this is an assignment operator, which means the weights are being updated to a new value each time. So gradient indicates the direction of increase or steepest descent. So the name gradient basically means to find the highest point instead of the lowest point. But as we want to find the minimum point in the valley, we need to go in the opposite direction of the gradient. So the gradients that we compute here are basically finding the highest point in our graph. But the purpose of machine learning algorithms is to minimize the cost function and find the lowest point. That's why we're moving in the negative direction and use the minus sign each time we update the weights. We update the parameters in the negative gradient direction to minimize the loss. So basically, the pseudocode describing gradient descent can be summarized as follows. First, we need to compute the partial derivative of the cost function with respect to each weight or each parameter, and we need the learning rate. J equal to 0 and j equal to 1 indicates the first and second parameter. And each time what we're going to do is what's known as simultaneous update. We're going to update each parameter by using the computed gradients. And each parameter has to be updated simultaneously, or we don't have to wait until we compute the first one in order to adjust the second one. The first thing that we have to do is compute the updates, the needed gradients, and we have to assign all of the parameters with the newly computed values so that we could carry out the simultaneous update. So if this is a cost function, then what we're doing when we are computing the gradient is finding the slope of the line at that point. So if it is greater than or equal to 0, and we're computing the derivative with respect to theta 1, here what we're getting is a positive number, because if the line is in this direction, then the computed gradient has to be positive. And if this is a positive number, then we have to, the negative sign basically says that move in the left direction, in the opposite direction. And this is basically guiding the model towards the minimum point. And if the computed gradient is less than 0, for example, let's say that we start from this point, we can see that the computed gradient is going to have a slope which is negative, because the line is in this direction. And since we will have a negative number for the computed gradient, and when we multiply it by another negative, it's going to be positive, so it's going to move to the right direction or in the positive direction to find the minimum point. So basically, if our cost function is a convex function and it's not sophisticated as this, it's going to basically find the global minimum point. But in reality, our cost functions are going to be complicated, and gradient descent might lead the cost function towards a local minimum and not the global minimum. And we will see that in the future slide. So we have talked about gradients in detail, but we haven't talked about the learning rate. Learning rate controls how much we should adjust the weights with respect to the loss gradient. So it basically decides how fast we adjust the weights with respect to the gradients. But learning rates are randomly initialized, and we try different learning rates until we find the one that works best for our model. We use the Greek letter alpha for learning rate, but there are other letters that we can use also, but for this case we use the letter alpha, and it helps in adjusting the weights with respect to gradient descent. The lower the value of the learning rate, the slower will be the convergence to the global minima. So for alpha, if alpha is too small, then gradient descent can be very slow, because we're basically subtracting a small number from theta, and each change will be very slow, and we don't want that to happen. And if alpha is too large, then for a learning if a higher value is used for learning rate, it will not allow the gradient descent to converge. So it may overshoot sometimes and even miss the global minimum, and it may diverge, so it bounces on and off from different points and overshoot the minimum. So we don't want alpha to be too small or too large, so we need a value for alpha that is between 0 and 1 most of the time. And gradient descent can converge to a local minimum even with learning rate alpha being fixed. So even if we fix alpha to a specific number, it means that gradient descent can also converge even if the value of alpha is fixed. As we approach the local minimum, the gradient descent will automatically take smaller steps. So as we get closer to the minimum point, gradient descent is going to take smaller and smaller steps until it basically becomes 0. And this is because that the computed gradients are going to be smaller and smaller even though that we have used a fixed alpha. Because if we use a fixed alpha, you might expect that in each iteration the steps we take must be the same. But since the computed gradients change as we move towards the global minimum and they get smaller, that means we don't need to decrease the alpha over time. But there are other algorithms which change the alpha over time. But in the case of gradient descent, we use a fixed hyperparameter alpha. And we have seen the difference between parameter and hyperparameters, and alpha is one kind of hyperparameter. So we need to differentiate between the local minima and global minima. Global minima is the smallest overall value of a function over its entire range. the loss function value reached a minimum globally over the entire loss function domain. So a global minima is basically the minimum or the lowest point across the loss function domain. There might be a lot of minimum points, but the one with the lowest value is known as the global minima, which is the throw of this function. But a local minima is the value of the loss function becomes minimum at that point in a local region, and it's a relative minimum but not a global minimum. It is a point where the function value is smaller than nearby but possibly greater than the lowest point. So it's basically greater than the lowest point. So if you start at a point which is closer to the local minimum, you're basically going to go and find that local minimum. And once you find that, gradient descent is not going to lead you to find the global minimum point. That's one drawback of the gradient descent algorithm, because as you reach the local minimum point, the computed gradient will be 0. And if it is 0, the slope will be a horizontal line. And when you multiply the learning rate by 0, you're basically left with the same weight once you reach this point, which means the weights are not going to be updated. So sometimes we might get stuck in the local minima while trying to converge to the global minima. And we will see how to solve this problem by using a different gradient descent algorithm. So basically there are 3 types of gradient descent. The first one is batch gradient descent or vanilla gradient descent. This is the one that we have discussed now. The second one is stochastic gradient descent, and the third one is mini batch gradient descent. The difference between these 3 types of gradient descents is depending upon which set of data set that we are using to train our models or to update the weights. So in the case of batch gradient descent, we use the entire data set to compute the gradient of the cost function for each iteration of the gradient descent and then update the weights. So we basically send all of the data at once and we compute the gradients so we send the data in a forward pass. Then in the backward pass for each iteration, we're going to send the whole data. So when computing the gradients, in order to update the weights using gradient descent, we're using the entire data set. That's why we're calling it the batch gradient descent. We're using a single batch. Since we use the entire data set to compute the gradient, convergence is slow. Since we are using the entire data set, it's going to be very, very slow in adjusting the weights. And if the data set is huge and contains millions or billions of data points, then it is memory as well as computationally intensive. If we use a huge data set that has a lot of entries, which might be millions or billions, then depending on the complexity of the data, even the number of features decide the complexity, and it might be memory wise and computationally wise very intensive. But advantage of batch gradient descent is for the theoretical analysis of weights and convergence rates are easy to understand. Since we are sending all of the data, there is nothing complicated about it, so it's easy to understand, but it has a lot of disadvantages. It performs redundant computation for the same training example for large data sets. Most of the gradients that we compute are going to be similar in each iteration since we are using the whole dataset. But if we are trying to use different parts of the dataset each time, the model is going to learn something new from each data. And it can be very slow and intractable as large datasets may not fit into memory. Our memory has a limit and we cannot use the entire dataset to train our model because of that limit. And it even affects the time needed to complete one epoch. So it might take a long time to reach one epoch. As we take the entire dataset for computation, we can update the weights for the model for the new data. Second type of gradient descent is stochastic gradient descent. So this is basically the opposite of batch gradient descent. Instead of using all of the data, we just use a single instance of the dataset. So we're going to use the first example, then we make a forward pass, and then we make a backward pass and update the weights. Then we use the second instance and then perform a forward and backward pass to update the weights. So each time we're computing gradients and we're updating the weight. And you can assume that when using batch gradient descent, since we are updating the weights once we use all of the dataset at once, it's going to be much smoother compared to stochastic gradient descent. This is going to have a lot of noise because we're computing different gradients for each instance. So instead of finding the local or the global minimum smoothly, it's going to have a lot of movements as we go along to find the global minimum. In stochastic gradient descent, we use a single data point or example to calculate the gradient each time and update the weights with every iteration. We first need to shuffle the dataset so that we get a completely randomized dataset. We have to shuffle the dataset so that we can randomize it and get different gradients each time. As the dataset is randomized and weights are updated for each single example, update of the weights and the cost function will be noisy and jumping all over the place as shown on the diagram. And random sample helps to arrive at a global minima and avoids getting stuck at a local minima. So random sampling helps us to find the global minima and helps us to avoid the local minima. So this is one method that we can use in order to escape the local minima so that we could find the global minima of the function. Learning is much faster and convergence is quick for a very large dataset. The learning is going to be much faster if you use a very large dataset. Since we are using a single instance each time, it's going to be much faster. So the advantages of stochastic gradient descent is that the learning is much faster than batch gradient descent. Redundancy is computation, computation is removed as we take one training sample at a time for each computation. The problem for batch gradient descent was that it was using the entire dataset, so in every iteration it's not going to learn something new and it becomes redundant. But in the case of stochastic gradient descent, that is not going to be a problem since we are using a single instance each time, and it's going to be very different because one instance is not going to be similar to another instance. Weights can be updated on the fly for the new data samples as we take one training sample at a time for computation. Since we're just using a single data in each iteration, is going to be very fast. The disadvantages of stochastic gradient descent is as we frequently update the weights, the cost function fluctuates heavily. So here you can see that it's very noisy when trying to find the global minimum. So in order to solve this problem, we use another type of gradient descent known as mini batch gradient descent. It's basically the midpoint between batch and stochastic gradient descent, which are the two extremes. In mini-batch gradient descent, instead of using each data sample, we're going to use a small batch of samples in order to compute our gradients and update the weights. So mini-batch gradient descent is a variation of stochastic gradient descent, where instead of using a single training example, a mini-batch of samples is used. Mini-batch gradient descent is widely used and converges faster and is more stable. This is the one that we're using when we're trying to build a neural network model. It converges faster because it's using a smaller portion of the data instead of the entire dataset, which is the case for batch gradient descent. And it's basically solving the noise problem from stochastic gradient descent because we're using a mini batch instead of each single instance. So the noise, there might be some noise, but it's going to be smaller when compared to stochastic gradient descent. So it basically solves the problems for both extremes, which is the batch and stochastic gradient descent. The batch size is the size of the mini batch that we're using. So in this case, our batch size is 3 because each mini batch contains 3 instances. And as we take a batch with different samples, it reduces the noise, which is variance of the weight updates, and that helps to have a more stable and converge faster. So batch size is another kind of hyperparameter because we're going to initialize it by ourselves. And by changing the batch size, we can find the correct number of the batch size that will help us to converge faster. So some of the advantages of mini-batch gradient descent is it reduces the variance of the parameter update and hence lead to a stable convergence. It speeds the learning and it's helpful to estimate the approximate location of the actual minimum. And the disadvantages of mini-batch gradient descent is that the loss is computed for each mini-batch and hence total loss needs to be accumulated across all mini-batches. Since the loss is going to be computed for each mini-batch, the total loss needs to be accumulated for all of the mini-batches because there are different losses and we need to consider all of the losses that are being computed. So let's put all of these side by side and try to see the difference. So if we have a training data X and it's vectorized, vectorization allows us to efficiently compute on M examples. So let's say we have M training examples. In the case of mini-batch gradient descent, we're going to partition the training set into mini-batches. In this case, our batch size is going to be 1000. Let's consider that the number of training examples in this case is 5 million. And if each mini batch is 1000, then basically we're going to have 5000 mini batches. The curly braces indicate the numbers for each mini batch, and xt and yt are going to correspond to each mini batch. So mini batch t, if t is equal to 1, it's referring to the first mini batch. So if x is the training data and y is the label, we can basically partition them by using the mini batch size, and we're using different kinds of nomenclature to differentiate between the training example and the mini batches. If we use parentheses, it means that we're indicating the training example, and if we use curly braces, we're indicating that we're talking about the mini batch. So in the case of the mini batch gradient descent, this is basically the code. So we're going to go through all of the mini batches from 1 to 5,000, and we're gonna perform forward propagation, a forward pass. In a simple linear regression algorithm, we're going to multiply the input data with the weights and add the biases and assign to z, and we pass in a couple of activation layers, which we're going to discuss in a future video. And finally, once we get the output, it's basically considered to be one forward prop. Then finally, after we perform the forward propagation, which we saw from our PyTorch workflow, then we need to compute the cost j, and this is a cost function. And once we compute the loss, we need to perform the backward step and compute the gradient. So we need to compute the partial derivative of the cost function with respect to each parameter. And in gradient descent, what we need to do is we need to update each weights by using the learning rate and the computed gradients. And this is what is known as one epoch on the training set. So each epoch is going to go through the 5,000 mini batches, since we have 5,000 mini batches. In the case of a batch gradient descent, it is going to use the entire training set for each epoch. But for mini batch gradient descent, we need two loops, one for considering the epochs, and the second one for going through each mini batch from 1 to 5,000. If you understand how this works, then it's basically easy to implement a simple model using either a batch or mini batch gradient descent. But in the case of PyTorch, you don't need to worry about implementing each step one by one, because PyTorch has specific functions which can perform a forward prop, which can compute the cost, computing the gradients, and also update the weights, which is basically the job of an optimization algorithm. So when we compare the batch and mini batch gradient descent, we can see that for a batch gradient descent, it's very smooth as we move towards the minimum. But in a mini batch gradient descent, there is some noise compared to batch gradient descent, but it's much more smaller when compared to stochastic gradient descent. So if the mini batch size is m, then here we can see that the blue line is converging without a lot of noise. But if we consider the mini batch size to be 1, there is going to be a lot of noise, because the mini batch size can be adjusted between we can use different sizes, but the two extremes can be, if we use the entire training set M as one mini batch, it's basically going to be considered as batch gradient descent, and it's going to be smooth as we move towards the minimum. If we consider the other extreme and consider the mini batch size to be 1, so we are considering each instance when computing the gradients, that is going to be stochastic gradient descent, and it's going to have a lot of noise. In practice, when we select the mini batch size, it has to be between the two extremes, which is between 1 and m.
Audio Jungle.